Let's start with the most basic question. What is interprocess communication? Interprocess communication, or IPC, is a mechanism provided by the operating system that allows two or more processes to communicate with each other. This communication may involve exchanging data, sharing resources, synchronizing their execution, or coordinating different tasks. Now, one important question arises. If two programs are running on the same computer, why can't they directly access each other's memory? The answer is memory isolation. Every process runs inside its own protected memory space. This protection prevents accidental data corruption, improves security, and keeps the operating system stable. Because of this isolation, the operating system provides secure communication mechanisms known as IPC. In modern multitasking systems, many applications run simultaneously. Without IPC, these applications would never be able to cooperate effectively. Now, let's understand why IPC is actually required. Imagine different applications running together on your computer. Sometimes they need to exchange information. Sometimes they need to work together on the same task. IPC makes this possible. It allows different processes to share data safely. It helps synchronize their execution so that tasks happen in the correct order. Processes can also notify each other whenever an important event occurs. In addition, IPC coordinates multiple internal activities within large software applications. Overall, IPC improves multitasking performance by allowing separate processes to cooperate efficiently without interfering with one another. Let's understand IPC using a simple real-life example. Imagine two employees working in separate office cabins. Each employee has their own notebook. They cannot directly write inside the other person's notebook. If they want to collaborate, they have two choices. The first option is using a shared whiteboard where both employees can read and write information. This represents shared memory. The second option is sending emails to each other. This represents message passing. Similarly, processes inside an operating system cannot directly access each other's memory. Instead, they communicate using IPC mechanisms provided by the operating system. Now, let's answer another important question. Why can't two processes directly communicate? The main reason is protection. Every process has its own private address space. This isolation prevents one process from accidentally modifying another process's data. It also protects the system against malicious software and unauthorized memory access. Without this protection, a small bug inside one application could easily crash the entire operating system. Therefore, direct memory access between independent processes is not allowed. Instead, all communication must happen through secure IPC mechanisms managed by the operating system. Real-life analogy. Consider students writing an examination. Every student receives their own answer sheet. No student is allowed to write directly on another student's paper. If any communication is necessary, it must happen through the teacher. In this example, the teacher represents the operating system. Just as the teacher safely controls communication during the examination, the operating system safely controls communication between isolated processes. There are two major models used for inter-process communication. The first model is shared memory. The second model is message passing. In the shared memory model, multiple processes access the same memory area. Because data is accessed directly, communication is extremely fast. However, synchronization must be handled carefully by the application. In message passing, processes exchange information through messages managed by the operating system. Although, this method is slightly slower because data needs to be copied, it is much safer and works well across different computers connected through a network. A simple way to remember this is shared memory is faster, message passing is safer, and more flexible. Now, let's understand shared memory in detail. In the shared memory model, the operating system creates a common memory region. Multiple processes are then allowed to attach this shared region into their own address spaces. Once attached, every process can directly read from or write to the same memory. Communication happens without repeatedly asking the operating system to copy data. The process consists of 4 steps. First, a process requests the operating system to create shared memory. Second, other processes attach to that memory. Third, all participating processes communicate by reading and writing data directly. Finally, once communication is complete, the process is detached from the shared memory, and the operating system releases the allocated resources. Because no unnecessary copying occurs, shared memory provides extremely high performance. Imagine a classroom notice board. Whenever the teacher places an important notice on the board, every student can walk up and read the same notice. Similarly, if a teacher updates the information, everyone immediately sees the latest version. Nobody needs their own copy. Everyone accesses exactly the same notice board. Shared memory works in exactly the same way. Instead of maintaining multiple copies of the data, all participating processes access one common memory region. Now, let's understand why shared memory is considered the fastest IPC method. Normally, when data is transferred between processes, the operating system must repeatedly copy information from one memory location to another. This copying consumes both CPU time and memory bandwidth. Shared memory eliminates these unnecessary copies. Once the operating system creates the shared memory region, all participating processes directly access the same physical memory. This significantly reduces communication overhead. It also minimizes system calls and lowers communication latency. As a result, shared memory becomes the ideal choice for transferring very large amounts of data, such as videos, images, scientific datasets, and large databases. Now that we understand how shared memory works, let's look at its advantages. The biggest advantage is high speed. Since all processes access the same memory region directly, there is no need to repeatedly copy data from one process to another. This significantly reduces communication overhead and improves overall performance. Another major advantage is high efficiency. Processes can instantly read and write shared data, making communication almost real-time. Shared memory is also the preferred choice when dealing with large amounts of data, such as high-definition videos, large images, scientific simulations, or massive databases. In short, whenever performance is the highest priority and processes are running on the same computer, shared memory is usually the best solution. Real-life analogy of shared memory advantages. Let's understand this with an example. Imagine 5 employees working on the same report. Instead of printing 5 separate copies, the company places one master copy on a conference table. Everyone simply walks to the table and reads the same document. No extra copies are needed. This saves both time and resources. Shared memory works exactly the same way. Instead of creating multiple copies of the same data, all processes directly access one shared copy, making communication much faster and more efficient. Disadvantages of shared memory. Although shared memory is extremely fast, it also comes with some challenges. The first challenge is synchronization. If 2 processes try to modify the same data at exactly the same time, the data may become corrupted. This problem is known as a race condition. To avoid this, programmers use synchronization techniques such as mutesys, semaphores, and condition variables. Another limitation is that shared memory only works between processes running on the same computer. It cannot directly connect applications running on different machines over a network. Finally, because every attached process accesses the same memory, a programming mistake in one process can immediately affect all the others. Therefore, shared memory is very fast, but it requires careful programming. What is a race condition? Narration. Now let's understand one of the most important concepts in operating systems. A race condition occurs when multiple processes access the same shared data at the same time, and at least one of them modifies that data. Because processes execute independently, the final result depends on which process finishes first. This makes the output unpredictable. The same program may produce different results every time it runs. Race conditions are one of the most common synchronization problems in concurrent programming. To prevent them, developers use synchronization mechanisms that ensure only one process modifies shared data at a time. Imagine 5 people editing the exact same Google document at the same time. If everyone starts typing on the same sentence simultaneously, they will overwrite each other's work. The final document may become confusing or even corrupted. To prevent this, people usually take turns or use editing permissions. Similarly, in shared memory, processes must coordinate their access using synchronization techniques. Without proper coordination, the shared data can easily become inconsistent. Race condition example, narration. Let's take a practical example. Suppose a bank account has a balance of 1,000 rupees. Process A wants to deposit 500 rupees. At the same time, Process B wants to withdraw 300 rupees. If both processes read the balance simultaneously before either one updates it, they will both perform calculations using outdated information. As a result, one update may overwrite the other. The final balance becomes incorrect. This is a classic example of a race condition. Always remember this exam point. Race conditions occur only when shared data is accessed concurrently without proper synchronization. What is message passing? Now, let's move to the second major IPC model, called message passing. Unlike shared memory, processes do not access the same memory region. Instead, they exchange information by sending structured messages through the operating system. The operating system receives each message, manages it safely, and delivers it to the intended process. Since every process has its own private memory, there is no shared state. Although message passing is slightly slower because data must be copied, it provides better security and is much easier to use across different computers connected through a network. This makes message passing the preferred communication model in distributed systems. Now, let's understand why message passing is so important. Modern operating systems run many processes simultaneously. These processes often need to exchange information while remaining completely isolated for security reasons. Allowing unrestricted access to another process's memory would create serious security risks and system instability. Message passing solves this problem. It provides a structured and secure communication mechanism where the operating system controls every message exchange between processes. This keeps applications independent while still allowing them to cooperate efficiently. Real-life analogy of message passing. Imagine 2 friends living in different cities. They cannot write inside the same notebook. Instead, they communicate by sending text messages or emails. Each message travels through the communication network before reaching the other person. Similarly, in message passing, processes exchange information by sending messages through the operating system. The operating system acts like the communication network, ensuring every message reaches the correct destination safely. Now, let's understand why message passing is so important. Modern operating systems run many processes simultaneously. These processes often need to exchange information while remaining completely isolated for security reasons. Allowing unrestricted access to another process's memory would create serious security risks and system instability. Message passing solves this problem. It provides a structured and secure communication mechanism where the operating system controls every message exchange between processes. This keeps applications independent while still allowing them to cooperate efficiently. Every message passing system is built around two basic operations. The first operation is send. The sender creates a message and transmits it to another process. The second operation is receive. The receiving process accepts the incoming message and stores it in its own memory. These two simple operations form the foundation of message passing communication. Whether applications are running on the same computer or across the internet, almost every messaging system ultimately relies on the concepts of sending and receiving messages. Now, let's learn about the two types of messages used in message passing. The first type is fixed-length messages. As the name suggests, every message has the same predefined size. This makes memory management simple and communication very fast. Fixed-length messages are commonly used for small control commands, status updates, and operating system instructions. The second type is variable-length messages. In this case, each message can have a different size depending on the amount of data being sent. This flexibility makes variable-length messages ideal for documents, images, videos, and other large or complex data. In simple words, fixed-length messages focus on speed and simplicity, while variable-length messages focus on flexibility. Let's understand this with a simple example. Imagine an examination. In the first exam, every student receives exactly 20 objective questions. Every answer sheet has the same format and the same number of questions. This is similar to a fixed-length message. Now, imagine an essay competition. Some students write 2 pages, while others write 10 pages. The size of every submission is different. This is similar to a variable-length message. The operating system chooses the appropriate message format depending on the application's requirements. Now, let's move to another important topic. Synchronous message passing is also known as blocking communication. In this communication method, both the sender and the receiver must participate at the same time. When the sender sends a message, it immediately stops and waits until the receiver accepts the message. Similarly, if the receiver is waiting for a message that has not yet arrived, it also remains blocked. In other words, neither side can continue until the communication is successfully completed. This creates a tightly coordinated communication process between the sender and the receiver. Let's look at the advantages and disadvantages of synchronous communication. One major advantage is reliability. Since both processes communicate at the same time, message delivery is immediate and predictable. Buffer management also becomes simpler because messages are delivered directly. However, there are some disadvantages. The sender must wait until the receiver is ready. If one process becomes slow, the other process also has to wait. This waiting reduces system performance and can even lead to a situation called deadlock, where two processes wait for each other indefinitely. Therefore, synchronous communication is best suited for applications where timing and accuracy are more important than speed. Synchronous communication is commonly used in systems that require immediate confirmation. For example, real-time industrial control systems use synchronous communication to ensure machines respond in the correct order. Banking systems also rely on synchronous communication. When you transfer money, the transaction must be verified before moving to the next step. client-server applications, and many network protocols also use synchronous communication whenever immediate acknowledgement is required. In all these systems, accuracy is more important than maximum speed. Think about a normal telephone call. You dial someone's number. Until the other person answers the phone, meaningful communication cannot begin. Both people must be available at the same time. If one person disconnects, the conversation stops immediately. This perfectly represents synchronous communication. Both the sender and receiver must actively participate together before communication can proceed. Now let's understand asynchronous message passing. This communication method is also called non-blocking communication. Unlike synchronous communication, the sender does not wait for the receiver. Instead, the sender places the message into an operating system queue or buffer and immediately continues its own work. The receiver collects the message later whenever it becomes available. Because both processes work independently, asynchronous communication improves overall system performance and concurrency. This is one of the reasons why modern distributed systems prefer asynchronous communication. Let's examine the strengths and limitations of asynchronous communication. Its biggest advantage is that processes do not waste time waiting for each other. This improves CPU utilization and allows many tasks to execute simultaneously. It also scales well for cloud computing and distributed systems. However, asynchronous communication requires message queues and buffers to temporarily store messages. If too many messages accumulate, the queue may become full. Managing these buffers also increases the complexity of the system. So, while asynchronous communication offers better performance, it requires more careful resource management. Let's understand asynchronous communication with another everyday example. Imagine you place an order on an online shopping website. The moment you click the Buy Now button, your request is accepted immediately. You don't have to keep the website open while your order is being packed. The warehouse processes your order in the background. Later, you receive notifications about shipping and delivery. This is exactly how asynchronous communication works. The sender submits a request and immediately continues with other work, while the receiver processes the request independently. This approach improves efficiency because neither side has to wait for the other. Now, let's compare synchronous and asynchronous communication. In synchronous communication, the sender must wait until the receiver accepts the message. This is known as blocking communication. Both processes remain tightly connected during the communication. Only a small buffer is usually required. However, there is a higher chance of deadlocks if processes wait for each other. On the other hand, asynchronous communication is non-blocking. The sender continues working immediately after sending the message. The receiver processes the message later from a queue. This approach requires larger buffers but offers much better scalability and performance. A simple memory trick is this. Think of a telephone call for synchronous communication. Think of an email for asynchronous communication. Let's look at some technologies that use synchronous communication. One common example is Remote Procedure Call, or RPC. In RPC, one computer requests another computer to execute a function and waits for the result before continuing. Another example is blocking sockets. Here, a program pauses until the required network data is completely sent or received. System calls also work synchronously. When an application requests a service from the operating system, it waits until the operating system completes the request. These technologies prioritize reliability and immediate responses over maximum speed. Now let's see the technologies that support asynchronous communication. Modern applications often use message queues such as RabbitMQ and Apache Kafka. These systems temporarily store messages and deliver them whenever the receiving application is ready. Another example is POSIX message queues, which are commonly used in Unix-based operating systems. Applications also use non-blocking sockets, allowing programs to continue execution even if network data is not immediately available. Finally, modern distributed systems frequently use event buses and the actor model, where independent components communicate using messages instead of direct function calls. These technologies make large-scale cloud applications highly scalable and reliable. Consider Amazon after you place an online order. As soon as you confirm the purchase, the website immediately displays an order confirmation. Your interaction with the website is complete. Meanwhile, several background systems start working independently. The warehouse prepares the package. The delivery partner receives the assignment. Tracking information is updated automatically. All these background activities happen asynchronously. This is why modern online services remain fast and responsive, even while performing many complex operations behind the scenes. In real-world software development, applications rarely rely on only one communication model. Instead, they combine both synchronous and asynchronous communication. This approach is called a hybrid communication architecture. Whenever the user needs an immediate response, the application uses synchronous communication. For tasks that can be completed later, the application uses asynchronous communication. This combination provides both responsiveness and high performance. Today, almost every large software platform follows this hybrid approach. Let's understand this using a food delivery application. When you place an order, the application immediately confirms that your payment was successful. This is synchronous communication because you expect an instant response. After that, many background activities begin. The restaurant receives your order. A delivery partner is assigned. Notifications are sent to your phone. Your live location is updated continuously. These background tasks happen asynchronously. Together, these two communication methods create a smooth user experience. Now that we've completed inter-process communication, let's move to another major topic in operating systems: process scheduling. Every computer has many programs running at the same time. However, in a single core processor, only one process can actually use the CPU at any given moment. This creates an important question. Which process should get CPU time first? The answer is process scheduling. Process scheduling is the operating system's mechanism for deciding how CPU time is distributed among multiple processes. A good scheduling algorithm keeps the CPU busy, improves multitasking, reduces waiting time, and ensures fairness among all processes. Without process scheduling, multitasking would simply not be possible. Imagine a hospital with only one doctor but many patients waiting for treatment. The doctor cannot treat everyone at the same time. Someone must decide which patient enters first. This responsibility belongs to the receptionist. The receptionist manages the waiting queue, gives every patient a fair chance, and ensures emergency cases receive priority. Similarly, the operating system acts like the receptionist. It continuously decides which process should receive CPU time next, keeping the entire system organized and efficient. The operating system performs scheduling to achieve several important goals. The first goal is maximum CPU utilization. The CPU should remain busy instead of sitting idle. The second goal is time sharing. The operating system rapidly switches between processes, so users feel that multiple applications are running simultaneously. Another goal is load balancing. Every process should receive a fair share of CPU time. Scheduling also aims to reduce response time, allowing applications to react quickly to user actions. It increases throughput, meaning more processes are completed within a given period. Finally, it minimizes turnaround time, which is the total time required for a process to complete after it is submitted. Together, these goals make the computer fast, responsive, and efficient. Now that we understand the goals of process scheduling, let's see how the operating system actually organizes processes. The operating system groups processes into different queues based on their current state. As a process changes its state, the operating system automatically moves it from one queue to another. This approach is called queue scheduling. Using queues helps the operating system organize thousands of processes efficiently. It reduces scheduling complexity, improves resource utilization, and allows the scheduler to quickly identify which process should run next. You can think of queues as organized waiting lines inside the operating system. Let's understand queue scheduling with a simple airport example. When passengers arrive at the airport, they don't directly board the aircraft. First, they join the check-in queue. After completing check-in, they move to the security queue. Finally, they wait in the boarding queue before entering the airplane. Each queue represents a different stage of the travel process. Similarly, inside an operating system, processes move through different scheduling queues depending on what they are currently doing. The operating system keeps everything organized by moving processes from one queue to another at the right time. The operating system mainly uses three scheduling queues. These are the job queue, the ready queue, and the device queue. Each queue serves a different purpose. Together, these queues help the operating system manage process execution efficiently. Let's understand each one individually. The first queue is the job queue. Whenever a new process is created or submitted to the operating system, it first enters the job queue. The job queue contains every process that has been submitted for execution. Some processes may still be waiting for memory. Others may already be running or waiting for resources. The job queue represents the complete collection of processes known to the operating system. A simple analogy is a university admission office. Every student application first enters the admission list before being selected for enrollment. Similarly, every process first becomes part of the job queue. The second queue is the ready queue. This is one of the most important queues in process scheduling. Processes in the ready queue have already been loaded into main memory, also known as RAM. They are fully prepared to execute. The only thing they are waiting for is CPU time. The CPU scheduler always selects the next process from this queue. Think of passengers sitting inside an airplane before takeoff. Everyone is ready to fly. They are simply waiting for clearance. Likewise, processes in the ready queue are ready to execute, but must wait for the CPU. The third queue is the device queue. Sometimes, a running process needs an input or output operation. For example, it may need to read data from a disk, print a document, or receive network data. Instead of occupying the CPU while waiting, the process moves into the appropriate device queue. After the ISO operation is completed, the operating system moves the process back into the ready queue. This allows the CPU to continue executing other processes without wasting valuable processing time. Now, let's understand how a process moves through the scheduling system. First, a new process enters the job queue. When sufficient memory becomes available, it is loaded into RAM and placed in the ready queue. The CPU scheduler then selects one process from the ready queue. That process begins execution and enters the running state. While running, several different situations may occur. Depending on what happens, the process either completes, requests an input-output operation, exhausts its time slice, or gets interrupted by a higher priority process. Let's discuss these situations one by one. The first possibility is that the process successfully finishes its execution. In that case, it simply exits the system. The second possibility is that the process requires an input or output operation. For example, reading a file or printing a document. Instead of waiting on the CPU, the operating system moves the process into the device queue. Once the I/O operation is complete, the process returns to the ready queue, where it waits again for CPU allocation. This efficient movement allows the CPU to remain busy while slower hardware devices perform their operations. There are two more situations that may occur while a process is running. The first is time quantum expiry. Many scheduling algorithms assign a fixed amount of CPU time to every process. When that time expires, the operating system interrupts the process and moves it back to the ready queue. This ensures fairness by giving other processes an opportunity to execute. The second situation is preemption. If a new process with higher priority arrives, the operating system immediately interrupts the currently running process. The higher priority process receives the CPU first, while the interrupted process returns to the ready queue. This allows urgent tasks to be handled without unnecessary delay. Now that we understand how processes move through different queues, let's discuss the components responsible for making these decisions. These components are called schedulers. Smidges are special parts of the operating system that decide when a process enters memory, when it receives CPU time, and when it leaves the system. There are three main types of schedulers: the long-term scheduler, the short-term scheduler, and the medium-term scheduler, which is covered in advanced operating system concepts. In this chapter, we will mainly focus on the long-term scheduler and the short-term scheduler. Let's begin with the long-term scheduler in the next section. Perfect. We're now entering the scheduler section, which is one of the most important topics for exams. I'll keep the narration smooth, engaging, and optimized for Quen custom voice. Let's begin with the long-term scheduler, also known as the job scheduler. The main responsibility of the long-term scheduler is to decide which new processes should be admitted into the system. When users submit programs for execution, those programs first remain in secondary storage, such as a hard disk or SSD. The long-term scheduler selects suitable processes from this job pool and loads them into the main memory, or RAM. Only after entering RAM can a process compete for CPU time. In simple words, the long-term scheduler acts like a gatekeeper. It controls which processes are allowed to enter the system for execution. The long-term scheduler performs three major responsibilities. First is admission control. It decides which submitted jobs should be loaded into memory based on the available system resources. Second is workload balancing. It maintains a healthy balance between CPU-bound and I/O-bound processes. This prevents either the CPU or the input-output devices from becoming overloaded or sitting idle. Third is resource management. It controls the number of active processes in memory, preventing excessive memory usage and maintaining overall system stability. These responsibilities ensure that the operating system runs efficiently under different workloads.
We need a perfect balance to keep things running. If everyone cooks, the food just piles up. But if everyone serves, there is nothing to eat. Balance is the key to a smooth operation.
Now, let's learn an important term: degree of multiprogramming. This simply means the number of processes currently loaded into main memory. The long-term scheduler controls this number. If too many processes are loaded into RAM, memory becomes crowded. The CPU spends more time managing processes than executing them. On the other hand, if very few processes are loaded, the CPU may remain idle because there isn't enough work to perform. Therefore, the operating system always tries to maintain an optimal degree of multiprogramming. This helps achieve maximum CPU utilization and overall system performance. Imagine a classroom with 40 chairs. If 150 students enter the room, it becomes overcrowded. Students cannot sit comfortably, and the learning environment becomes chaotic. Now, Imagine only 5 students sitting in that same classroom. Most of the chairs remain empty, which wastes available resources. The ideal situation is somewhere in between. Similarly, the operating system maintains an optimal number of active processes in memory to ensure both efficiency and stability. Now, let's compare 2 important types of processes. The first is a CPU-bound process. These processes spend most of their time performing calculations. They require long periods of CPU execution and generate very few input-output requests. Examples include video rendering, scientific simulations, and mathematical computations. The second type is an I/O-bound process. These processes spend most of their time waiting for input or output operations, such as reading files, downloading data, or printing documents. The operating system tries to maintain a proper balance between these 2 types. A good mix keeps both the CPU and the input-output devices busy, resulting in better system performance. Unlike the CPU scheduler, the long-term scheduler does not run continuously. Loading a process from disk into RAM is a relatively slow operation. Therefore, the long-term scheduler runs only when necessary. For example, it runs when a new job is submitted. It also runs when several processes finish execution and free up memory. Additionally, it may run whenever the number of active processes falls below an efficient level. Because these events occur occasionally, the long-term scheduler operates much less frequently than the short-term scheduler. A poorly designed long-term scheduler can significantly reduce overall system performance. If it loads too many processes into memory, RAM becomes overloaded. This increases paging activity and may even cause thrashing, where the system spends more time moving data between RAM and disk than executing actual programs. On the other hand, if too few processes are admitted, the CPU remains idle because there isn't enough work available. The scheduler must therefore maintain the right balance between available memory and active processes. This balance is one of the key responsibilities of the long-term scheduler. Now, let's move to the second scheduler, the short-term scheduler, also called the CPU scheduler. Unlike the long-term scheduler, this scheduler works continuously. Its job is to select one process from the ready queue and assign the CPU to it. Every time the CPU becomes available, the short-term scheduler immediately decides which process should run next. Since these decisions happen extremely frequently, the short-term scheduler must be very fast. It operates in milliseconds and plays a major role in ensuring smooth multitasking. The short-term scheduler performs several important tasks. Its primary responsibility is CPU allocation. It selects the next process from the ready queue according to a scheduling algorithm, such as first-come, first-served, round-robin, or priority scheduling. It also performs context switching. Whenever one process stops and another begins, the scheduler saves the current process's state inside its process control block, or PCB, and restores the saved state of the next process. This allows processes to resume exactly where they left off. The scheduler also maintains fairness, prevents starvation, and ensures interactive applications respond quickly to user input. Because of these responsibilities, the short-term scheduler is one of the busiest and most critical components of the operating system. Let's continue exploring the responsibilities of the short-term scheduler. Apart from allocating the CPU, it also ensures fairness among all processes. Every process should eventually get a chance to execute. Without fairness, some low-priority processes might never receive CPU time, a situation known as starvation. To solve this problem, operating systems often use a technique called aging. In aging, the priority of a waiting process gradually increases over time. Eventually, every process gets its turn. The short-term scheduler also keeps the system responsive by giving quick attention to interactive applications such as keyboard input, mouse clicks, and user interface events. This is why modern operating systems feel smooth and responsive even when many applications are running simultaneously. The short-term scheduler uses different scheduling algorithms to decide which process should execute next. Some of the most common algorithms are first come, first served, where processes execute in the order they arrive; round robin, where every process receives an equal time slice; shortest job next, which selects the process requiring the least execution time; priority scheduling, where higher priority processes execute before lower priority ones; and finally, multi-level queue scheduling, where processes are divided into different queues based on their characteristics. Each algorithm has its own advantages and is chosen according to the system's requirements. Now, let's understand when the short-term scheduler becomes active. The scheduler is triggered whenever the CPU becomes available or a scheduling decision is required. One common situation is when a running process requests an input or output operation. Since the process can no longer use the CPU, the scheduler immediately selects another ready process. This ensures that the CPU never remains idle while waiting for slower hardware devices. Efficient CPU utilization is one of the main objectives of process scheduling. Another important event is timer expiry. Many scheduling algorithms assign a fixed amount of CPU time to every process. This fixed interval is called the time quantum. When the time quantum expires, the operating system generates an interrupt. The currently running process is temporarily stopped and moved back to the ready queue. The scheduler then selects another process to execute. This mechanism ensures fairness because every process receives an equal opportunity to use the CPU. Round-robin scheduling is one of the most common algorithms that uses this approach. Another event occurs when a process finishes its execution. Once the process completes all of its instructions, it releases the CPU. The operating system removes the completed process from memory. The short-term scheduler then immediately selects another process from the ready queue. This continuous cycle allows multiple programs to execute efficiently, even though only one process can actually use the CPU at any given moment. Now, let's consider another situation. Suppose a process is already running. Suddenly, a new process with a higher priority arrives. Should the operating system continue executing the current process? The answer depends on the scheduling policy. In preemptive scheduling, the operating system immediately interrupts the current process and assigns the CPU to the higher priority process. The Brayed-Demino-Welbiand use hope. This approach ensures that urgent tasks receive immediate attention whenever necessary.